Questions 21 to 25 on the 2010 Grade 9 Pascal Math Contest. In the diagram, each of the 5 boxes is to contain a number. Each number in a shaded box must be the average of the number in the box to the left of it and to the right of it. What is the value of x? Well, I'll call this A and I'll call this B, and let's proceed. So A, according to the rules of the question, is 8 plus B divided by 2. B is equal to A plus 26 divided by 2. So we've got 2 variables, 2 equations we can easily solve now. So this one gives me 2A is equal to 8 plus B, and therefore B is equal to 2A minus 8. I can sub that into there, and that gives me 2A minus 8 is equal to A plus 26 over 2. Cross multiply by 2 and you get 4A minus 16 is equal to A plus 26. And therefore 3A is equal to 42. And therefore A is equal to 14. And we can substitute that back into here to get B. And if you do, you get 2 times 14 minus 8 is equal to B. So that's 28 minus 8, which is 20. So now we can concentrate on the last 3. It means that 26 is equal to B plus X divided by 2. Well, B we just figured out was 20. And then divide by 2. Cross multiply, you get 52 is equal to 20 plus X. And therefore X is equal to 32. So number 21, the answer is D. A rhombus PQRS is inscribed in a rectangle JKLM. As shown, a rhombus is a quadrilateral with 4 equal side lengths. Segments PZ and QR are parallel to JM. Segments QW and YS are parallel to JK. If JP is 39, JS 52, KQ is 25. What is the perimeter of rectangle WXYZ? All right, let's start labeling. JS is 52 from there to there. And then JP is 39 and KQ is 25. Okay. And I guess because this diagram, the way they've drawn it with parallel lines, that means PW is also going to be 25 there. And SZ will be 39. And I guess we can immediately figure out that since this is also going to be 52, WZ will be 52 minus 25, so that's 27. Okay, I think we got actually a lot of it already. XZ is going to be 27 since that is a rectangle. So now we just have to figure out WX, and that's going to be the same as ZW, and that's it. Okay, I think I can do that. Well, I'm going to concentrate first on this triangle. That Pythagorean relationship, 52 squared plus 39 squared, will be SP squared. And if you do that, you get 2704 plus 1521 is SP squared. And if you solve for this, you get SP is equal to 65. So that is 65 right there. Now it's a rhombus, 4 equal sides. So that means this is 65 also, since that is equal. And then now I can use Pythagoras again on either of these triangles. It doesn't really matter. I'll just use it on this one right here. So that means 25 squared plus WQ squared is equal to 65 squared. So that means this is 625 plus WQ all squared is equal to 4225. And therefore, if you solve, you get WQ equal to 60. So now we have to figure out that just this WX from there to there. Okay, so this whole thing is 60. So Wx is the final piece of the puzzle. That's basically just Wq minus Xq. But because of the fact that this is a lot of symmetry here and similar triangles, you can deduce that Xq is the same as Sz. This is the same as this, because these two triangles are the same in terms of their angles. So if Xq is the same as Sz, Sz from there to there is the same as Jp. And that is 39. So we plug that back into this formula, Wx. Wq we just got was 60. Xq we just realized was 39, and therefore Wx is 21. So there you go. This is 21, this is 21. And therefore the perimeter of that rectangle is 21 plus 21 plus 27 plus 27. And that is, if you add those four numbers up, 96. So number 22, the answer is D. The product of n consecutive 4-digit positive integers is divisible by 2010 squared. What is the least possible value of n? So they're saying you've got some numbers, there's n of them, and they're all 4-digit numbers, and when you multiply them together, you've got this big long product, and it divides by 2010 squared. It gives you some integer. Okay, no problem. So that means that this number in the numerator has to include all of the prime factors of 2010 squared. So that is the first task of figuring out what is 2010 broken down into prime factors. It's 2 times 3 times 5 times 67. So if you have 2010 squared, it's basically 2 times 2 times 3 times 3 times 5 times 5 times 67 times 67. So this numerator up there has to include all of these guys. If it does, when you divide by 2010 squared, it will give you an integer. Okay, so let's figure this out. First and foremost, this is a very important point that they're 4-digit numbers. All the numbers that I put in my numerator, they have to be 4-digit numbers. So I have to first start off with creating a 4-digit number from these prime factors. And if you notice, these are very small numbers. Interestingly, even if you take all of them and you multiply them together, you actually still don't get a 4-digit number. You get 900. So the only way to get a 4-digit number that includes the prime factors is to involve the 67s. So obviously one such number would be 67 times 67. That's definitely going to be one such 4-digit number, and that number is 4489. Now, I think the challenging part of this question is that you can also create another 4-digit number as a reference point by including a 2. Because if you do 2 times 67 times 67, you will also get another 4-digit number that can be used, and that's 8978. You can't go any higher, because if you started using 3s and 2 67s, you would no longer have a 4-digit number. You'd have a 5-digit number. You'd have 13,000 something. So these are the only two 4-digit numbers. So my string of 4-digit numbers that I put in my numerator has to be somewhere plus or minus those numbers. So first, let's just start with this guy here, and let's see what we get. All right, so we're going to start with 4489. Now, I don't know which direction we're going. Are we going greater or are we going less? So I'll just write in a few on either side. All right, now let's play this game here. My task is to involve all of these guys into a string of numbers that obviously includes 4489 as my sort of reference point? Well, let's see. Okay, so I've got to ensure that every single one of these prime factors is included in the numbers that I choose. So I'm starting with 4489. So 4489 is obviously divisible by 67. It was 67 divided by 67. 67 times 67. So that means this guy takes care of this guy and this guy. Okay? Now we can go in either direction. We can go this way or that way. It doesn't really matter. I'll just go this way and then we'll see what happens. 4488. Well, that is obviously divisible by 2. And it's divisible by 2 once again. So it takes care of 2 2's. Now, can it be divisible by anything else? And the answer is yes. It can also be divisible by a 3. So this one helps us out quite a bit. 4487. Is that divisible by any of the remaining 3? 4487 is not divisible by 5, obviously, because it would have to end in a 5 or a 0. And it's also not divisible by 3. So that's a loser. How about 4486? Does that help me in any way? Is it divisible by 3? It's not. So that's a loser also. How about 4485? Is that divisible by 3? Yes. Is it divisible by 5? Yes. So this takes up that one and that one. Now, if I go in this direction, that's obviously divisible by 5 since it ends in a 0. So there you go. This string of 1, 2, 3, 4, 6 numbers, they're consecutive 4-digit positive integers, and when you multiply them all, they will all contain those factors which represent 2010 squared. So far, the answer looks like it could be 6. And in the answer choices, 6 is the second smallest. Oh, I see. So, it's possible that 5 could be the answer, so we got to keep going here, unfortunately. I was hoping that 6 was the smallest, but it's not. Okay, so let's go in this direction now. All right, we're going to obviously keep this 4489 because that takes care of 2 67s. Now let's go to 4490. 4490 obviously is divisible by 5, so that takes care of 1 5. And is it divisible by anything else? It is by 2. And then anything else? No, unfortunately. So far, we have those two. 4491, does that contribute or help us in any way? Is it divisible by 3? The answer is yes. So that takes care of 1 3. And it's divisible by 3 again. So I can circle another 3. 4492, obviously that's divisible by 2. Since it's even. And I think that's it. And then we've got this one lone 5, and unfortunately I have to go all the way to include this guy, and this guy to get a number that's divisible by 5, which is this. So that would mean 1, 2, 3, 4, 5, 6, 7. Oh, now I got n equals 7. So that's worse, because they want the least possible. Okay, so this is the part of the question that I think is tricky. We have to now do the same story for this guy. And that being 8, 9, 7, 8. Okay? And same thing, we got to go in either direction. So 8, 9, 7, 8, this middle number, it was 67 times 67 times 2. So it takes care of those ones. Now let's go this direction. Doesn't really matter, but let's just go in that direction. Does that help us in any way? Is it divisible by 3? It's not. Is it divisible by 2? No. And is it divisible by 5? No. So that doesn't help us at all. How about 8, 9, 7, 6? It's obviously divisible by 2 since it's an even number. And then, is it divisible by 3? And the answer is yes. And anything else? No. So we got a couple of prime factors. How about 8, 9, 7, 5? That is obviously divisible by 5 because it ends in a 5. Then it's divisible by 5 again. And is it divisible by the final 3? No. But what about 8, 9, 7, 4? Is that divisible by 3? And the answer is no. Okay. Well, what if I go in this direction and try the 8979? Is that divisible by 3? And the answer is yes. So look at that. By using this guy, I got a string of only 5 numbers that include all the prime factors of 2010 squared. So the answer is n equals 5. So number 23, the answer is A. A sequence consists of 2010 terms. Each term after the first is one larger than the previous term. The sum of the 2010 terms is 5307. When every second term is added up, starting with the first term and ending with the second last term, the sum is. We have some terms, x1, x2, and so on, right? All the way until you get to 2010. There's 2010 terms. And they're saying that this whole thing is equal to 5307. Now let's discuss what it is they want us to figure out, which is right here. Every second term is added, starting with the first term and ending in the second last term. So they want us to find x1 plus x3 plus x5 all the way up until the second last term, which is x 2009. What is this sum? Okay, to get that, what we have to do is rewrite this one as follows. x1 is fine by itself, but x2 is really just x1 plus 1, right? Because each term is 1 greater than the previous. x3 is fine by itself, no reason to change that, but x4 is x3 plus 1. And similarly, x5 is fine by itself, but instead of writing x6, we can write x5 plus 1. So I hope you understand what's happening there. And then you just keep on going like that, all the way to the very end, which would be x 2009, which is fine to be written like that, but then instead of x 2010, we'll write x 2009 plus 1. And this is, of course, 5307. Now, when you write it like this, you can start grouping. So, for example, you'll notice that the x1 appears twice. So you have 2x1, and then the x3 appears twice, 2x3, and so on, all the way up to x 2009. That appears twice. But then you have all these ones that need to be added. 1, 1, 1. And how many of those are there? Well, there's 2010 terms, and the 1 appears every other term, so half of the time. So 1005 of those ones. Okay, 2010 divided by 2, basically. So this is what we're down to. Now here you can factor out a 2, and if you do, you get x1. I'll write it in blue here and makes it look a little bit more obvious. x1 plus x3 plus x5 plus ... plus x 2009. And don't forget that 1005 at the end right there, 5307. And this is what they are asking us to find. So pretty straightforward here. I can just isolate this now. Since I've got it, it would basically be 5003.07 minus this 1005 divided by 2. And that would be this whole thing, x1 plus x3 plus x5 plus ... until the second last term, which is exactly what they want. And if you do that math, 5003 minus 105 divided by 2, 5307 minus 105 divided by 2 is 2151. So that is what goes here, 2151. And therefore, number 24, the answer is C. 6 soccer teams are competing in a tournament in Waterloo. Every team is to play 3 games each against a different team. Note that not every pair of teams plays a game together. Judine is in charge of pairing up the teams to create a schedule of games that will be played, ignoring the order and times of the games. How many different schedules are possible? We've got 6 teams, right? A, B, C, D, E, and F. 6 teams. And there's several ways, of course, but we'll just go in a logical order. We have A playing 3 games, and then similarly, all the other teams have to play 3 games, so B, 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 and so on. So let's just make this simple for us. Let's say A plays B, then plays C, and then plays D. Okay? That means so far A has played 3 games, so A is done. Now B has played 1 game already, so that is counted right there. But now B has to play 2 more games. And in a very similar way, C is right here. It's already played A, so 1 game has already been counted. C has to play 2 more games. So we've got a couple scenarios. The first scenario is when B and C and D, which is the same story. D has already played 1 more game. D has to play 2 more games. Those 3 teams that are right here, B, C, and D, don't play each other. If they don't play each other at all, then they must play the other teams, which are E and F. So that makes it pretty straightforward. B therefore plays E, and B plays F. C plays E, C plays F. And D plays E, and D plays F. So let's do the count here. B has played 3 times, B is done. C has played 3 times, C is done. D has played 3 times, D is done. And similarly, E, 1, 2, 3, F, 1, 2, 3. So all of these guys satisfy. So this is one possible scenario, right? Now, the good thing about this is that I chose A as my starting point, right? But what about this? This was B, C, D. This represents just one way of choosing 3 teams from the remaining 5. A is my starting point, and then I've got to choose 3 teams from the remaining 5. That was just one possible scenario. How many such scenarios are there? Well, from 5 teams that are right here, you have to choose 3. So it's 5 choose 3. And 5 choose 3, if you're not familiar with factorial notation or choose notation, it's 5 factorial over 2 factorial over 3 factorial. And that is equal to 10. So that means that this scenario that I just drew right here has 10 possible ways to create. So what I'm going to do on the side here is just sort of keep a little tally here of how many different cases. So we'll just call it tally. And so far we have 10. The answer choices are all greater than 10, so obviously we've got a little bit more work to do. But we have 10 so far. Okay, we continue with this question in pretty much the same way. Now we do the exact same story. We have 6 teams, A, B, C, D, E, F. And we want to create the same kind of story, so I'll write it all again. And again, just like before, I'll just put B, C, D here. It's any of those 10 ways is fine. But now the scenario is going to be different than this. And I'll explain that in a minute. Now we get to a point where we have to start talking about what do we do next. And before, B, C, and D don't play each other. That is the scenario that we chose. Now we choose a scenario where B, C, and D can play each other. So what I can do, A is already played 3 times, so A is done. B's played once, so this one is done. But now I've got to figure out, where do I go next? Well, I can let B play C, like that. There's only 3 ways that B can play C, or B could play D. Those 3 letters, in terms of B, C, and D, can only play each other in 3 ways, right? The first way, of course, is what I just drew, which is BC. And the other way would be, of course, BD. And of course, the other way is CD. So this gives me 3 possible paths that I can take, starting with one initial path. So that means that of all these 10 initial paths, I've got 3 more branches. And those branches are this guy, and this guy. So right off the bat, I've got 30 different paths that I have created, and each of those creates a new schedule of games. Okay, so I hope that makes sense. I'm just going to concentrate on this one right here, BC. Now at this point, what do we do for B? B, can it play D? Because it has to play one more, right? Because I've got so far that B has played 2 games. This one here and this one here. So it's got to play one more. But can it play D? And the answer is no, because if you try that scenario, what will end up happening is that the E's and the F's are left in a situation where it's impossible for them to play 3 games. So that means that B and C, the only thing we can do is have them play E and F. So we'll just create one such scenario. You can have B play E, and when you do that, B is done. You got 3 games for B right there. And then we continue. C has already played A here, and C has already played B there. So C's done, but we got one more game for C. Make it play F. All right, so C's done. 1, 2, and 3. Now D already played A here, so we don't need to talk about that guy. But then D will obviously have to play E and F to pick up 3 games. And then so far we have, let's see, E and F have already played 2 games each. So obviously they need one more game, and therefore E will play F. And that's it. E is 1, 2, and 3, and F is 1, 2, and 3. So this scenario is great. It all matches up. So what I did up here was I created the scenario BE and CF, if you notice. There's one other scenario that is just switching the F's like this, BF and CE. So what this does is it gives you 2 possible directions of these 30. So my tally now is 30 times 2, which is 60. So recount the totals. From this scenario where B, C, and D don't play each other, we have 10. From this next scenario where B, C, and D can play each other, we have 60. So the total is the 10 up there plus the 60 down here, and that is 70. So the answer to this question is 70, and number 25, therefore, is E.